in the last class, which is electromagnetic induction. As we mentioned last time, this is the topic which connects electricity with magnetic properties. And just to have a quick recap, most of the EMI is based on Faraday's experimental law. And this was the kind of setup what Faraday used to arrive at the law. So we will not go into detail, but in terms of law, the law is whenever magnetic flux through area bounded by a closed loop. What are we talking about? A closed loop, a plane surface. So it is a surface. So whenever magnetic flux, how do we calculate magnetic flux? Same way we calculate electric field flux. So suppose we have an area here, and there's some magnetic field, uniform magnetic field exists in this space. Suppose the magnetic field is like this. How would I calculate flux through this area? I'll draw the area vector. Area vector is perpendicular to the plane, and in open surface, the direction is immaterial. So if this is the direction of area vector, and this is the angle theta, so we can calculate magnetic field flux will be equal to what? This will be equal to B vector dot area vector. And this is the same definition earlier. So we can calculate, and this term is called magnetic flux. And if the flux changes through this area, so what will happen if the flux changes, there's EMF induced in the loop, which is equal to rate of change of flux. So what we need to understand, yes, we are talking about an area bounded by a loop. If there's a magnetic field, there's a flux. And if flux is changing, there's induced EMF, the loop will behave as if there's a battery connected in the loop. And EMF of that battery will be equal to minus sign. We find out the direction using Lenz law. We only find out magnitude using d phi by dt. The rate of change of flux is equal to EMF induced. Okay, and this is the definition. And we dealt with the unit also. Unit of flux should be a Tesla meter square, which is written as Weber. Okay, so EMF produced, and if EMF is produced, if there's a loop, if the loop is a conductor of resistance R, so suppose we take a wire and form a loop with the wire, and if this wire has resistance R, if there's a magnetic field and somehow we make the flux change, there are a number of ways we can change the flux. We'll come to that later. There are three quantities involved when we calculate flux here. There's a magnetic field involved, there's area involved, and there's angle between them is involved. So any three can change. Field can change, area can change, and angle can change. So whichever way, any of the three change in any of the three quantity can lead to change in flux. And if flux changes, there's induced EMF. And if there's a coil has resistance R, if there's induced EMF, it will behave as if there's a battery connected of EMF equal to d phi by dt, and it will produce current I. Current I is equal to EMF by R, R being the resistance of the loop. We'll add one more small thing here. So if in this, what is I? I is equal to charge is equal to dq is equal to I dt. So if I take the dt term in here on this side, this term becomes equal to, so if I take dq, this term becomes dq, dq is equal to I dt is equal to 1 by R d phi. Okay. And if I integrate this term, what do I get here? This you get delta q, and this term is total, say 1 R by common. So this term indicates change in flux. So what is charge flow? Charge flow in a loop is equal to change in flux divided by the resistance. Okay, so so charge flow is independent of time. What we notice here, so suppose if there's a change, we'll come to some numericals also, perhaps you will understand relationship better. But what we notice here mathematically, what we find, the charge flow is equal to, so whenever there's a change in flux, it leads to current. Current basically means there's a flow of charge. Okay, so current is rate of flow of charge, and suppose you want to find out in a given time interval, what is the total charge flow? The total charge flow will depend on, in that time interval, what is the change in flux. And charge flow is equal to change in flux in that time interval divided by R. That's the charge flow. Okay, so that's what we interpret this equation as. And let's look at, so today we'll spend some time applying this basic formula or basic understanding. Let's see, this is what is given here. Okay, let's look at, yes.
So once can you go to the previous slide, sir?
Yes.
What does charge flow mean, sir? Like, it's in the
What
same
is
loop, right?
in the same
Charge
loop?
flow.
Yes. So any cross section. See, what is the charge crossing? See, with if we take the loop, anywhere we take the cross section, will the amount of charge crossing any cross section will be different?
It has to be same.
It has to be same. The current everywhere loop is same. So what is the charge crossing a given section? See, what is current? Current is equal to rate of flow of charge. If I multiply current by time, it becomes charge flow in a small time interval. And if I take a larger time interval, it becomes charge flow in that time interval. So what is delta Q? It is charge flow in some time interval delta T. During the time interval, what is happening? The flux is changing by delta phi. So these two quantities are related. And let's take one example and how do we find it out? Okay, so let's take this one. So here the square loop PQRS is given and it has resistance R. It is placed near an infinite long wire carrying constant current I. And this is constant current I. And yes, all this information is given. The loop is rotated by 180 degree about an axis parallel to the long wire. So this loop about this axis is rotated by 180 degree. If I rotate by 180 degree, what is the amount of charge that will pass through any point of the loop during rotation? So that's a question. So let's look at this. So what we need to do whenever we rotate by 180 degree. So first of all, let's start with the initial state. Again, I think some of you started. Okay, while somebody is doing some annotation, somebody is writing something and creating some sign. Okay.
SB final minus initial.
You'll come to that part. I think somebody has written something on the screen. I'm just erasing it off. Okay, note.
So you can see who wrote it, like.
It doesn't matter. I say whosoever is written, I don't think anybody is done on purpose, so it's okay. Okay. Okay, let's see what we see. How do we approach this question? What is the total amount of charge that will pass through? I will look at this. This is the total amount of charge that will pass through will be equal to 1 by R into change of flux. Now it doesn't matter how much time it has taken for flux to change. Change of flux is equal to initial flux and final flux. So let me first start. What is initial flux? Initially, when I look at this, so I can take area some direction. Area vector, let's say it is what is direction of field? Field is cross field. Let's say area vector also perpendicular to the plane into the same direction. So if I take that direction, initial, what is theta value? Initial theta is equal to 0, which is angle between B vector and A vector. If I rotate by 180 degree for corresponding to final position, if initial angle I take as 0, final angle will become equal to, final theta becomes 180 degree. So if initial flux is equal to BA, final flux will become equal to minus BA. So whenever we rotate by 180 degree, so whenever this is something happens, whenever a coil is rotated by 180 degree, starting from area vector and starting whenever rotated by 180 degree, with initial, what are the initial condition here? With initial B perpendicular to the plane. Okay. In that case, change of flux will be equal to twice the initial flux. And that makes common sense. BA mere change in flux will be equal to 2BA. So what I need to do here, all this case, to calculate change in flux, I need to calculate what is the initial flux. Can I calculate initial flux here? What is initial flux here? If I take initial flux is equal to BA cos theta. But if I take different, here the field is not constant. So what I need to do here, how to calculate flux here?
We take an elemental strip.
We take an elemental strip. Okay. So we take an elemental strip and let's take an elemental strip because we have to take a strip over which field is constant. Field is varying as a distance from here. So I take elemental strip at a distance x of width dx. So to calculate initial phi, so we take elementary strips. So I'll calculate d phi. What is d phi in this case? Angle is cos theta is equal to 1 because field is perpendicular to the plane of the loop. So d phi will be area into B. What is B at a distance x into area? What is B into dA? B at a distance x is equal to mu naught into I divided by 2 pi x. And what is the area here? This side is A and width is dx. So this will be A into dx. That's the flux for small strip. So what will be the total flux? Add it up over this entire area. If I add it up, so this x is a variable, x is varying from where? X is varying from A to 2A. So it will be integration from A to 2A. And that's a fairly simple integration. Rest of the term I take it out. It is mu naught IA divided by 2 pi is the constant term. It's integration of dx by x from A to 2A, which will give you to log 2. So mu naught I by 2 pi into log to the base E 2. That's the flux. So what will be my charge flow be equal to? Change in flux equal to twice the initial flux and divide by 1 by r. I'm not concerned about direction. The question also doesn't ask about the direction. 1 by r into delta phi. Okay, I'll write it here. So what is dq equal to? I just substitute 2 into initial flux. That's the change on flux divided by r. So that will be equal to, and r being, resistance is small r. So 2 divided by small r into initial flux is equal to mu naught I by 2 pi log to the ES 2. Okay, so that's how we calculate. And what would happen what would happen to current? Now we can rotate this coil in 1 second, we can rotate in 0.1 second, we can rotate in 10 seconds. All cases the charge flow will be same. But what will happen if I rotate it very quickly, same charge flow in a smaller time, the current will be large here. And if I rotate it slowly, charge flow is same, but the charge flow is taking place over a time interval of 10 seconds, and the I will be small. So current will depend on time it has taken for flux to change. But charge flow for given initial flux and given final flux, charge flow is independent of time it has taken for flux to change. Okay, so I'll just some of you may have some doubt about 180-degree rotation. So I'll just explain what happens in case of 180-degree rotation. So as initially this is R and S, and as we start rotating, suppose we start rotating like this. So if I look from the top, this side R dash will come like this. As theta is changing from 0 to 90 degree. What will happen if I look from the top is
area decreases.
Yeah, so the side projection also you can see from the top. What will happen? This side will keep narrowing. R will move from here to this side. So what will happen in this case? In this case, the area is decreasing. Flux will decrease. Here, flux is decreasing, and direction of magnetic field is like this. If flux is decreasing, what will the direction of charge flow? What will the direction of current? So I hope you understand this is the direction of field. So here, as we rotate, the area will keep on decreasing. If area decreases, flux will decrease. Hence, induced current will be in the same direction. So that will be the direction of induced current. If this induced current, charge flow will be from where to where? Charge flow is from R to S. That's how the charge will flow in this branch. We'll try to understand first half of rotation and second half of rotation. So this is 0 to 90 degree. How would area look like when the angle it has rotated by 90 degree? If I'm looking from the whole, this square from the top, how would this square look like when it is rotated by 90 degree? Total I rotate by 180 degree. It will look like a line. This is what it will look like at theta is equal to 90. And just try and think, suppose you have this kind of, you can take any square shaped frame and try to rotate. What will happen after 90 degree? Which side this point R will be? Initially the point was on the right hand side if I'm looking from the top. After 90 degree, which side the R will appear? On the left hand side. And R will move like this. I understood after I rotate by 90 degree, when theta is 90 to 180 degree, R has come onto this side. Now what is happening? The flux is increasing. If the flux is increasing, the direction of current also will change. This becomes direction of current. But what is the direction with the charge is flowing? Charge is string flowing from R to S. So as I rotate from 0 to 180 degree, the direction of charge flow always remains same. That's why we add it up. So that was the point I was trying to make. So as I rotate from 0 to 180 degree, direction of charge flow is the same. If we continue rotation beyond 180 degree, then what will happen? The direction of current flow charge flow will reverse. And by the time I complete total rotation of 360 degree, what will the total charge flow if I rotate from 0 to 360?
0.
0. So 0 to 180 one direction, 180 to 360 opposite direction. And I did with this diagram, I was just trying to explain why from 0 to 180 degree, whatever direction of charge flow I have from 0 to 90, same direction continues from 90 to 180 degree. After 180 degree, it will reverse.
The current will also not change, no, sir. Direction of current.
If the direction of charge flow is not changing, direction of current also is. See, if I take a particular side here, 0 to 90 also, this was the direction of current. 90 to 180 also, this is the direction of current. Okay.
Yes, sir.
See, if you look from the top, you may feel that left hand side, the current was in the upward direction. In this case, that the left half the current is in the downward direction. But what has happened? The sides also have interchanged. So direction of current, if I take any two particular point in the loop, so that's why I mark this point R and S. Between point and RS, direction of current is still the same. Let's look at some simpler question. We can just go through this a little simpler one. A coil has 100 turns and area. The plane of the coil is at the right angle to magnetic induction. So let's try and understand. Suppose this is how the coil is. It can have any shape. I have drawn as a rectangle. It doesn't matter. So this is a coil. So how do we represent the plane of the coil is at a right angle to magnetic field? This is the plane of coil. It means field is like this. If field is perpendicular to the plane of coil, it means angle between area vector and B vector is equal to 0. Theta is equal to 0, or you can take as 180, doesn't matter. Theta is equal to 0. Both cases you get the same answer. Thus what is given here? The coil is rotated through 180 degree. So by now we already know when the coil is rotated by 180 degree in 0.2 second, what is the average EMF induced? Let's look at this, what this question is about. So what is about average EMF? We know what is EMF equal to. EMF is equal to, see, we'll always calculate magnitude. We'll find direction using Lenz law. So whenever we apply Faraday's law, we take the magnitude separately, direction whenever required. Then only we use Lenz's law. In this case, direction is not relevant here. So what is the EMF, this induced EMF? This is, what does this indicate? This indicates instantaneous EMF. And so what will be the average EMF?
Delta phi by delta.
Delta phi by delta. So in this case, what is delta phi? Delta phi is twice the initial flux divided by time.
Sir.
Okay, all we need to do is calculate what is initial flux. Let's say what is initial flux is equal to. Flux is equal to is a B vector, A vector into cos of theta. And if their number of turns NA. So it is equal to flux is equal to NBA cos theta. Let's put those values. What are those values here? 1000 turns. B is given as 2 into 10 to power minus 5. Area is given 10 to power 4 converted to SI unit. And initial cos this theta is equal to 0. So this is pi and twice of this. So to calculate EMF, so I twice phi divided by delta t, we can find this EMF here. So this all this thing is a part of your homework. You can do in the you can easily calculate. Next part also is very simple. A closed coil with resistance R is placed in magnetic field. Flux linked with the coil. That's other term what we use. Flux is also sometimes we say flux linked with the coil is fine. If magnetic field is suddenly reversed in direction, the charge flow. If flux is whenever magnetic field is reversed, so cos theta term will become whatever value of cos theta I had, it will become negative of that. So whenever magnetic field is reversed, delta phi will be equal to, this also the same case, delta phi is equal to twice the initial flux. What is change in flux here is equal to, if initial flux was a phi, it will become minus phi. So if I so change in flux, I could have written like this also. Initial flux, change in flux is equal to final flux minus initial flux. Okay. So final flux will equal to minus phi and minus with the initial flux. It will see whenever it reverses, it will become equal to, and we are always calculating magnitude. It's not asking about the direction. The magnitude of change in flux will be twice the initial flux. So this also is a fairly simple question. Change in flux is equal to 2 phi. And charge flow will be equal to how much? So delta Q will be equal to how much? Charge flow is equal to 1 by R times the change in flux. That's all. That's the answer.
Sir?
Yes?
Sir, I have a doubt in the previous slide.
Yes?
Yes, sir. Sir, I didn't understand what the number of turns. No, sir, I mean the next slide.
Okay. This question?
Yes, sir. I didn't understand what number of turns has to do with the flux.
Flux, okay. Let's understand here. See, suppose there's a number of, if n turns means there are n coils.
Yes, sir.
Each coil has same area, same orientation, same field. Flux is a scalar quantity.
Yes, sir.
So I calculate, so what is B dot A is flux through one coil. All coil, if they are wound, how many 100 coils, 1000 coils here? So we are just adding up the flux to each coil.
Yes, sir.
It's a scalar quantity. That's why I can add it. I think this term, and we have come across somewhere earlier also in case of magnetism, but yes, that's what it is. It's a scalar quantity. And even if it was vector also, when coils are turned here, all will point in the same direction. Even if it's vector quantity, we could have directly added.
Yes, sir.
Okay. So whenever I have 1000 turns, we take each one as independent and add it.
Sir, when this change in flux, the current will be induced like instantaneously, or?
Yeah, what does this mean? What is the EMF is an instantaneous value. At an instance, what
So
is
it's like action reaction pair or something?
Action and reaction pair, is it appropriate to use the term? This is something like cause and effect.
Cause effect. Cause effect, yeah.
Not action and reaction.
So there will be some delay.
Yeah, no, there's actually, it happens very quickly. It happens in a matter of nanoseconds.
Yes.
Okay. So it's a response. See, when we create a field in any conductor, how much time does it take for charge flow to develop? Practically instantaneously. So this also has similar effect. So any particular instance, both are, there's no lag, there's no latency. As soon as the flux changes, at that particular instance, EMF develops, which is directly related to rate of change of flux at that particular instance. Both
so
are
current will be exactly as long as how much difference there is.
Pardon me?
The current induced will be as long as the flux is changing.
Correct. Right? And so the EMF also has instantaneous value. So current also will have instantaneous value. If rate of change of flux is not constant, EMF also will not be constant. And we'll come to that case in case of rotation. We'll come to that case also now. We'll see one by one. Let's look at some bit of Lenz's law. In this case, what is given? Consider a metal ring kept on a horizontal plane. This is a metal ring. A metal ring means it has free charge, current can flow. This is a metal ring. And let's see the axis of metal ring is kept on a horizontal plane, so axis is vertical. A bar magnet is held above the ring with this length along the axis of the ring. So axis, this is how the bar magnet is placed. If magnet is dropped freely, if we release the magnet here, had the metal ring not been present, this would have an acceleration of g. Why would have acceleration of g? Mg force would have acted, no other force would have acted. Now there's a metal ring here, and I assume that metal ring is fixed in place. So if I drop this bar magnet here, will it move with the same acceleration g, or will it have lower or higher acceleration? Can anyone answer what would be the acceleration of this bar magnet if it is released with this length along the?
It will be lower, sir.
Why it will be lower?
Lesser, sir, because of Lenz force.
Yes, that's what Lenz force says. What will happen? This is something it will because of as soon as if there's a bar magnet here, it will create field through the coil, magnetic field. As it start moving, what will happen? Field creates, it will create flux. As it moves closer, what will happen? Flux will change. As flux will change, there will be induced current. And there's induced current, it will create a field and it will exert some force. But all those things are, there's a long chain of, a long sequence of things which will happen. But if we apply the Lenz's law in very simple form, why there is a induced current here in this? Because the bar magnet is moving closer to the ring. How it will oppose that cause? By applying a force, by repelling it. It is trying to come close, it will try to repel. If it is trying to, if the change is, it is going away, it will try to attract. So here, the force exerted because of current in the ring and all will be in the opposite direction. Hence, it will have lower acceleration.
So the bar magnet is like a moving charge.
Bar magnet is actually, this something is not easy. It's not moving charge. All bar magnets you can think of as a moving charge, a current coil, but we are not looking at that. But basically, okay, you can think of a bar magnet, think of a moving, you can think of a current loop. How we can think of bar magnet? As a current loop. I'll come to one more question later on current loop also. See, there's something, but if we don't overanalyze, if I don't overanalyze, what I think here, what will happen between the two? Flux is changing. So basically there's induced current and some forces, the magnetic forces may develop. Because this also is like a current carrying loop. This also current carrying loop. There are two current carrying loops. Depending on the direction of flow in the two loops are in the same direction or opposite direction, it will have attractive or repulsive force. So I can visualize the bar magnet as what? Current carrying loop.
Right.
So it will have some forces. How it will oppose? It will oppose by applying a force will oppose the change. The change is motion towards, force will be repulsive. So it will, acceleration will be, what will happen after it is fallen through? What I mean by fallen through, let me change that part also. Now it has, suppose after some time the bar magnet has passed through the loop. Now it has gone below the ring. Suppose the ring is kept here and by now this is how the bar magnet position.
It will still be less than G.
Which direction now magnetic force will act?
Upwards.
Now it is going away. So what will try to the force, Lenz's law, it will try to attract. So even now also the force which is acting is opposite to direction of mg. So whether it is falling from the top or it is falling below, both cases the acceleration will be equal to less than g. And this we take, and what happens, this is one way of analyzing this. If a ring is there, and if actually there are, I think I'll find some nice examples, some I think some video also available of a similar experiments conducted, and gives an idea how would it happens. And it is used very, this kind of applications are used in several industrial applications are also there. So some of the things I maybe will talk about a little later. So I'll give one more example of this. In place of a ring, suppose there were numerous rings. Suppose I make numerous rings, infinite number of rings, all same radius concentric rings. What would the shape look like?
Cylinder.
Cylinder. So rather than ring, suppose I have a cylinder, which is a metal cylinder. In this is a long cylinder. It's a long cylinder. So if I drop a bar magnet, it is passes through metal cylinder. Will the bar magnet acquire a terminal velocity? Yes or no, and why? We can't calculate. Will the bar magnet reach a terminal velocity? Think of why, and will the bar magnet reach a terminal velocity?
Its weight will be equal to Lenz force.
So first of all, what does terminal velocity mean? As soon as I release the bar magnet, it will have downward acceleration g. Only force acting. As soon as I release, it will have downward force mg. No other force acting. That's why there's a downward acceleration. But as soon as it requires velocity, what we understand here, higher the velocity is, greater is the rate of change of force, and as the v keeps increasing, fb also will keep on increasing. Important point what? So as bar magnet, velocity increases, FB also keeps increasing. So is it something, have you seen something similar happening elsewhere? Something is dropped and it initially starts with acceleration equal to G and it gains velocity, velocity keeps increasing. Where have you come across
Free
something
fall,
similar?
sir.
Huh?
Free fall.
Yeah, we have come across exactly something similar of if you drop a small spherical metal ball in a liquid. There also viscous force acts. Viscous force is proportional to velocity. This force also is dependent on velocity. As the velocity increases, rate of change of flux through the coils here keeps on increasing, and the force also keeps increasing. And any force keeps increasing, at some point in time, these two forces become equal and opposite. It acquires a terminal velocity. So it will fall with a constant velocity if the cylinder is long enough.
So how is
Shamini, are you following
velocity?
so far? Shamini,
Yes, sir.
are you following so far or going over the head?
I'm following, sir.
Okay. Let's look at one more application of Lenz's law. Just read the question, then we'll draw a figure. Okay, there are two identical circle coils A and B. I hope you understand what does this dotted mean. See, actually these two coils are perpendicular to the plane of the figure. This side is nearer to us, this side is away from us. This is something that's only we can visualize in 3 dimension. And this is something, this is the direction we are sitting at. Okay. The two coils AB placed parallel to each other. If I take this x-axis, axis of the coil is along x-axis with the centers on the same axis. The coil B carries a current I in the clockwise direction as seen from A. So where are you observing it from? You are observing from A. So clockwise means if I look at the nearer side, the direction of current should be upwards or downwards so that it appears clockwise. A person stands from here. If the person is observing from A side, this side will be on the right side of the person or left hand side of the person, this coil, this side. There are two halves of the circle. This half is nearer to us, this half is away from us. This side will come on the right hand side of the person. So right hand side, what if it is clockwise, what has to be the direction of current as seen from A? If it is clockwise, this has to be the direction of current. It has to be in the downward direction. Okay. That's the direction in the current and this is how the current is. But same thing if you look from here, that's what I think important point is. If a person is standing on one side of the current, from here it looks clockwise. If you look from other side, it looks anti-clockwise. That's the reason why we do not use anti-clockwise and clockwise as the sign convention for circular motion. We use omega. In this case, what is the omega vector direction? If it is blue, suppose there's a particle which is moving in like this. In that case, omega vector direction, whichever direction, it will be I cap. So that's why we use anti-clockwise and clockwise, depends on which side direction you're looking at. Suppose the clock also what you have is transparent. If you look from behind the clock, the needle of the clock will appear to be moving in anti-clockwise. So this is the direction. From here it looks clockwise. Now what is the question here? What would be the direction of induced current in A seen from B when the current in B is increased? This current is increased. How do you find direction of current in A? If this is a current I.
So field is increasing along x direction. So flux is increasing.
If I is
along
increased.
X direction.
In B. Okay, so what will be the direction of current in A as seen from B? There are two ways of thinking. One way I can do in terms of force. Okay, if current is increasing, what will be the nature of force between A and B, attractive or repulsive? As per the Lenz law. Shreya, can you tell me what should be the direction, the force between A and B? If the current is increased, will the force between A and B be attractive or repulsive? Shreya?
It should be a red.
See, what is happening when current is increasing means what? Flux is increasing or decreasing if the flux increases? See, if the current increases, flux increases. How do you oppose the increase in flux in terms of force? By pushing it, bring it closer, or forcing it away?
Forcing it away.
Away. The force would be repulsive. If force is repulsive, see that the force is repulsive when the current is in the same sense or when it is in the opposite sense. When is the force repulsive? If two so the direction of current, so opposite, repel. So what has to be the direction of current? For repulsive force, the direction of current has to be in the opposite. So if it is like this, the direction here is opposite. Disha, have you understood this point so far?
Yes, sir.
Huh? So direction of current in the opposite sense.
Yes, sir.
But whether it's clockwise or anti-clockwise, it depends on I'm viewing from here or here. So this is the direction of current in A. Now let's look at what is asking. Direction of induced current is A as seen from B. If I observe from here, how would the current look like? If I observe from here, suppose some observer is standing here. First of all, direction in B would look like what? Direction in B as seen from A was clockwise. As seen from here, it is direction of current in B is anti-clockwise and direction of A is clockwise. So if I observe from here, the direction in current A, direction in loop A will be clockwise. So second thing, what happens if the coil B is moved towards A? Will it produce similar effect or opposite effect? If you move towards A also, it will produce the same effect as this also will lead to increase in flux. As increase in I also is leading to increase in flux. When I move B towards A also, it will have the same effect. So direction of induced current in both cases will be same. It will be clockwise, clockwise. This is the answer. Bhageshri, have you understood?
Yes, sir.
It will be anti-clockwise, right?
Which one? See, clockwise and anti-clockwise, again, let me repeat. See, what is direction of current in B? As seen from A, clockwise. But if I see from here, if from this side it appears clockwise, from this direction, what is the direction of B? It will appear like?
It's as seen from the underside.
B is anti-clockwise. From here, if I look at current in B is anti-clockwise for this observer. And direction of current in A is opposite. So when B it is anti-clockwise, the direction current A as seen by this observer will be clockwise. Ashray, have you understood?
Yes, sir, I got it.
Got it. Okay. Now we come to something like AC generator. Okay, rotated with frequency. Let's try and understand what does it mean. And suppose we have a number of coils. And let's say we draw this coils. Initially, the coil is placed in XY plane. And this coil can rotate about this axis here. And initially, the magnetic field, this magnetic field is in the vertical direction. And we take this the area vector also normal to the plane. We can take in any direction. Let's take this area vector also in the same direction. So when I rotate this coil, so initially what I notice here, what is the angle between A and B? So let's say at time t is equal to t naught. Angle between area vector and magnetic field vector is equal to 0. Now when we start rotating with angular velocity omega. If angular velocity is omega at time t, what will be the angle between them at time t? Angle between two vectors will be how much?
Omega t.
Omega t. So if I want to calculate phi as a function of time, here the phi is a function of time here. So can I calculate what is the flux at time t?
BDA.
No, actually flux is equal to what? Number of turns into B into area into cos of angle between them. Let's put those values. It will be N B into A into cos of omega t. Is this flux constant? What is changing here in this case? What is changing in this particular Gayatri? What is changing here? So what is induced EMF here? Gayatri?
Yes, sir.
d phi by dt. What is changing in this case here? Why is the flux changing in this case when I'm rotating the coil here? What is causing the change in flux here? Angle between area vector and B vector is changing. B is not changing, area is not changing. Orientation is changing. So if you differentiate, what we get here? Minus omega NBA sine of omega t. So what do you notice here? If I rotate with the constant velocity, angular velocity omega, will the EMF instant, this gives you average EMF or instantaneous EMF? It's a function of time. It gives you instantaneous EMF. How is EMF varying here? So if I rotate the coil, this is what the EMF which is generated, which varies as a sine function of time. So if I interpret this equation here, if by some means, it is not easy, I have to rotate, I have to apply some torque here to rotate this coil here. Okay, so when I rotate this coil with angular velocity omega, it will generate EMF which will vary as a sine function of time. And this is nothing called, that's how AC power is generated. So what is the method of generation? Rotate the coil at the constant angular velocity. This is EMF generated. What you have to find, what is the maximum value of EMF? So there we are concerned only about magnitude. So one will be EB maximum. E maximum when sine of omega t is equal to 1, which magnitude will be equal to omega times NBA. That's the maximum EMF generated. Okay, and what would be the orientation when maximum EMF generated? At that time, omega t is equal to pi by 2 is equal to theta. So theta has to be 90 degree. So maximum EMF is generated when theta is equal to 90 degree. That is the time when actually flux is 0. So EMF rate of change of flux is maximum when the flux is 0. Does it make sense?
Yes, sir, it makes sense.
Yes. Okay. So let's look at this question. This is 2018 question. See whether this question and the question above are almost same or not. Well, that's why I put in the same sheet. All of you read this question and see whether they are almost same. So what you have done at the center of fixed large coil of radius r. This is large coil of radius r. A small coil of radius r is placed. Two coils are concentric and are in the same plane. The large coil carries current I. So this coil is fixed and current also is fixed. If current and coil is fixed, this coil is small, it means the magnetic field through the small coil is equal to constant. What is B equal to mu naught I by twice the radius of the large coil. And what is the direction? And it is perpendicular to the plane of the coil, which means I can assume initial theta is equal to 0. Exactly the same situation as above. Only difference is here value B is given. Here in place of B, what we need to write? In place of B, I need to write mu naught I by 2R. Rest all is same. So here also, if I calculate what is the EMF induced as a function of time, EMF induced as a function of time, exactly the same. It will magnitude, since here this question also is not talking about direction. So it is talking about magnitude because you're not defining direction in coil. Okay. So magnitude will be omega times N into B into A into sine of omega t. Now, what are things we need to substitute here? Omega is okay. Two coils are connected. Is there a number of turns? Number of turns are not mentioned, so N is equal to 1. What is value of B we need to substitute here? B is the
by 2R.
mu naught I by 2R. And what is the area we need to substitute? Area of the coil here. Radius of coil is given as r. So the area of coil will be equal to pi small r square into sine of omega t. That's the expression. So this is the same question, only thing small twist what they have done. Rather than giving a small constant value of B, the constant value of B has been given in slightly different form. It is given the B value is same as magnitude. B value is equal to field created by large coil at its center. Let's look at this question. Circular loop of radius r, resistance is r. The circular is forms a complete loop. And variable magnetic field induction B is equal to mu naught by T is established inside the coil. And we have to calculate what is the electric power developed right after closing the switch. Basically, what we need to calculate, we need to calculate power at time t is equal to 0. What is power equal to? This R is given here resistance. What is power equal to? I can write power as I square R or B square by R.
Yes, sir.
So all I need to do, I need to calculate value of EMF at time t is equal to. First, I have to calculate EMF as a function of time. If I calculate EMF as a function of time, I can easily answer this question. How do you calculate EMF as a function of time? Let me write this EMF as a function of time. So we have to calculate this value of V, which is nothing but EMF. I can write as EMF E square by R. And what is E equal to? Instantaneous value of E is equal to d phi by dt. Is the flux given here? Let's calculate what is the flux as a function of time. Flux is equal to BA into cos theta. If their number of turns are not mentioned, number of turns are one only. So is the value of B given? Yes, the value of B is given as a function of T. So phi will be also a function of theta. What is the area given? Circular loop radius R, pi r square. And what is the angle between them? Cos theta is equal to 1. This is phi t. So can I calculate EMF for E value, EMF induced as a function of time? Is equal to d phi by d phi dt. Yeah, again, in most cases, we don't bother about the negative sign. We find the direction of current flow using Lenz law. We only calculate magnitude using this relationship. So how much that comes to? Pretty simple.
Sir, EMF will be equal to the V, sir.
Yes, what is the, see, what does EMF mean? We'll come to that point again. See, this whole circuit will behave as if there's a battery placed of EMF equal to induced EMF. That's why using the word induced EMF. Is the battery present? No. But the circuit will behave because of flux changing in the loop. This circuit will behave as if there's a battery of EMF given by d phi by dt.
About so two adjacent points.
Yes. So that becomes simple. So B naught E square e raised to power minus t. Negative sign doesn't matter because we are taking modulus only. So this is the EMF induced. So what would be my, what is induced at time t is equal to 0? E at time t is equal to 0 is equal to how much? Pretty simple. Pi r square B naught. So what is the power at time t is equal to 0? E square by R. R is the resistance, this R is the radius. So that will be pi square B naught square R4 by R. Okay, let's look at this figure here. Maybe I'll draw, but this is a question given. I'll just redraw the figure. So what you see here, this boundary, this is the boundary within which there's a uniform magnetic field B. It doesn't matter, I have changed the direction, I know purpose, I didn't notice, answer remains same both cases. So there's a uniform magnetic field, outside there's no magnetic field, inside there's a magnetic field. There's a triangular loop here. The shape of the loop is in form of a triangle. with apex angle of 90 degree. The frame starts entering the region of uniform magnetic field with a constant velocity v. So at time t is equal to 0, it starts entering here. Okay, and this has velocity v. And this is a position at certain time t. So at time t, I want to find out at a random time t what will be the EMF induced. So I have taken this shape. So what will the x coordinate of the apex if at time t0 it started entering? So x coordinate here will be equal to this. I take as x-axis. What is the x coordinate at time t? So at time t, what are you trying to do? Method what you are trying to do here is we'll find phi as function of time. And once we find function of t, then we can find EMF also as a function of time, which is d phi by dt. And once we have E as a function of time, I can find I also as a function of time, which will be EMF induced as a function of time divided by R. This is a method I'm going to use. So first, what is the starting point here? Because you have to calculate I. For I need to EMF. For EMF, I need change in flux. For change in flux, I need phi. So what is phi at time t? That's what I need to calculate. Phi will be equal to B into area which is there within the magnetic field. So this is the area what I need to calculate. Can I easily calculate this area? If I take this side is x, this angle is 45 degree. So this side also will be x. So what is the area which is, so what if to calculate flux is equal to B into area, not this area. Because this area, there's no magnetic field. So entire area of triangle we are divided into two parts. Though this is the entire loop, this loop, there's no flux. This loop only there's a flux. So what is that area equal to? Very easily can calculate area is equal to x square. So the flux becomes equal to B into x square. What is x? X is nothing, okay. So this is B into x square. If I differentiate, so this is flux as a function of time. So EMF will be equal to d phi by dt. So what is d by dt of bx square? 2bx dx by dt. Or we can write as this is v. So 2b into x also is equal to vt, and dx by dt also is v. So that's the EMF induced 2b v square t. So what will the current as a function of time? This is how the current it will vary. So what we notice here, the EMF will keep increasing with time. It is linearly increasing with time. So what will happen to current? Current also is the EMF by resistance. Resistance is given. Okay, it doesn't matter. Resistance is constant. See, will the resistance change? Here only part of the loop is inside the magnetic field.
Resistance won't change.
Resistance won't change. The current has to flow the entire loop. Doesn't matter whether part of the loop is inside or part of the loop is outside. If part of the loop is inside, the flux will depend on how much part of the loop is inside. But current will not depend on what part of the loop is inside. Current will flow through the entire loop. So this R is constant here. So what we notice here, this is what the current will be, 2b v square T by R. Okay. And actually, if we will calculate BLV later, okay. And this will be equivalent to if this length of rod L is moving velocity v. I'll come to this point later. I think we will do that part also. So which graph is valid? This graph is valid. And how long this will continue? What happens after some time? The entire triangle will be inside. Once the entire triangle is inside,
it becomes constant.
It will become constant. So after a while, it will become constant.
So
will I become constant?
No, sir, it'll be zero.
Flux will become constant. So once entire triangle is inside, when entire loop is inside, flux will become constant.
And then current will become zero.
Current will become zero. If flux becomes constant, it means rate of change of flux is zero. It means EMF is zero, and I is equal to zero. So what will happen as soon as the whole thing becomes outside, this will become like this. And what will happen when you start going out?
It will decrease. The current will decrease. And it will be negative current below the graph.
It will flow in the opposite direction. So whatever shape we draw, it will flow in the opposite direction. And Okay. The current will be something like this. So if I draw the shape, it will be something like this. It is like this. As soon as it drops to 0, and from here it will be something like this. Again drop to 0 when it's fully out. This is time fully inside, and this indicate completely outside. Okay, let's think of two more cases where just before we end. Let's say this length is L, is a rectangle, and this length is 2L, and this length is other orientation is different, 2L and L. Both are moving with a constant velocity. In which case, which you think the maximum EMF will be more? This case or this case?
Second case.
Second case will be more. Maximum EMF will be more. The rate of change here, the length becomes this, area becomes more. Here it will be like this, and here it will be like this. The area becomes more. For same velocity, rate of change of area will be greater here. Hence, the rate of change of flux will be greater. Hence, the rate of current also will be greater. So this will be EMF induced will be twice of this area. And will this, if I draw first case, what is the shape of EMF time graph if it is moving the constant velocity?
It will be parallel to x-axis.
It's parallel to x-axis. So here what is happening, here it is changing. So here if I draw the curve here, it will be something like this. It remains 0, and when it's going out in the reverse direction. If this is for first one, this is for loop A, loop B will be twice that value, but it will be for half the time. But it will be for the
Half the time.
half the time. Will the charge flow in both cases be same?
Yes, sir.
Charge flows in both cases will be same. Here the current is twice as much, but it is for half the duration. This is the shape for A loop. This will be the shape for B rectangle. Okay, so that's what time we had today. And
Sir?
yes.
Sir, in the previous question, I didn't understand how the current is more for B loop.
This question you are not understood?
Yes, sir.
This question or previous? You are talking about this question?
This question only, sir.
You calculate EMF. So suppose again do the same thing exactly. Let's take it has this something. How much length is inside? Let's take an instance with how much length? X length is inside. What is the flux at this instance? What is the flux? X into 2L is the area. Field is B. Cos theta is equal to 1. Okay. So what will the EMF now?
dx2 will be.
So if EMF will be d phi by dt, which will be B into 2L into B.
EMF.
That is this is in this particular case. What will happen in this particular case? This particular case, it will be like this. And so what we notice here, this case, EMF is independent of X. Asha, what does independent of X mean here? The X term has not come.
Yes.
So it doesn't matter whether it's 1 mm is inside or whatever. So right from the time it has entered till the time it is fully inside, the EMF will be constant. Previous case, what you notice here, how was the EMF here? When you calculate EMF.
Okay. Yes, sir.
This was dependent on X.
Yes, sir.
So as X keeps increasing, it will keep on increasing linearly. So I think we need to understand this expressions also. It's a function of X. This is V term. I could write this is X. This is Vt by written, but this is X. It's a linear function. It's a function of X. So X keeps increasing. The area keeps becoming more. So rate of change of area also keeps becoming more here. And there's another way also we can deal with some question, similar question that we are going to do tomorrow. Okay. So that's the time we had for today. So a little bit